let's state it in the simplest form. Okay. So, we are not going to prove this today, just we are going to state it. And we are going to build up the things which will help us prove this. So, what does it say? Sorry. Matrix is diagonalizable. Before even we finish the statement, we must define what is an orthogonal matrix, because that is necessary in defining this. So, orthogonal matrix. What is this? P n cross n G L m R. Actually, orthogonal matrix could be defined over any arbitrary field because we don't need spectral theorem or positive definiteness to define this one. So such that P transpose B is equal to identity. Does it mean P transpose is also identity? Yes. Why? Well, if you take the transpose, what do you get? Yes. Yes. P transpose. All right.
So what the thing that you can write multiply P transpose, yes, and take P transpose inverse on both sides, you will get identity and P transpose.
Yeah, sure. So this follows. I mean, this is also you can only P transpose equal to identity by the uniqueness of inverse. So now we can finish the statement of vector theorem, at least in the simplest form. So this is the simplest form. Our real symmetric matrix is diagonalizable in the following manner. There exists an orthogonal matrix P such that P transpose is diagonal. So you not only have something like P inverse, you can also say what is something more about this matrix. It's an orthogonal matrix. Moreover, all the eigenvalues of A of the real symmetric matrix is eigenvalues of A are real. So it says three things. It's diagonalizable. The matrix which diagonalizes, you can choose the matrix which diagonalizes it to an orthogonal matrix. And the third thing is that all the eigenvalues are real. So that's the statement, as we said, in the simplest form, because we are not talking about matrices over complex numbers or Hermitian forms. Actually, we have not defined what is a form yet. Yeah.
Transpose just because you choose the combination that P inverse in that diagonal.
Right. And this P transpose is the inverse of P. Yes. If it is orthogonal.
Diagonalizable means it's P inverse is equal to
Right.
P inverse is equal.
Exactly. And since it's an orthogonal matrix, we can write P transpose. So here we define what is the bilinear form. Yes.
Why is this the simplest form?
Oh, because here we are taking real symmetric matrices. Then we can take actually complex Hermitian matrices. And then instead of orthogonal matrices, we use IISER unitary matrices. In fact, this is true for some, more generally, we can take normal matrices. So there are several generalizations of this. What is a bilinear? Let's see what is a bilinear form. From P cross P to F. F is the defining field. Bilinear forms we can define for arbitrary fields. Once we try to define positive definiteness, we have to come to the case of reals or so it's just a map. Earlier for duals, we're considering just a map from V to F, a linear map, and now we are considering a map from P cross V to F. So that bilinear means that it is linear in both coordinates. So if call this map F such that it should satisfy these properties, F of say V W plus W prime would be F of VW plus F of VW prime, then F of V plus V prime W, this will be F of VW plus F of V prime W, then F of CV and VW, this will be just CV times F of V. There C for all C and V in the field F, over which this vector space is defined. So V is a vector space defined over something. Alright. What do you mean by bilinear? That it is linear in each component. Similarly, you could define multilinear maps. Okay. Now, something which is related with this, but we still do not need to go to reals. We can still do it on arbitrary fields. We are going to define what is a symmetric form. So it's a bilinear form, and now we are going to define what is a symmetric bilinear form. Perhaps you could already see what we mean by symmetric because it has
that means V and W and
exactly. Yeah.
it maps to the same number.
Yes, right.
Like a dot product, right?
Yes. Indeed. That's actually the base example of this.
Also, sir, that P transpose P is equal to I you defined as an orthogonal matrix, right?
Yes.
Yeah. So the matrices are orthogonal in what sense? Like, what's the rationale behind them? What it?
You will see it soon. Yeah, I mean.
So what was the example of the bilinear?
Okay, so the example that Farun just gave is that take the first example is dot product. So consider both of these as Rn and Rn and this as R. Then the dot product is a perfect example of this. Another example. So that's example 1. Another example, so example 2. We just wrote down something a little ago. That is, we are taking this sum of this matrix vectors. If you recall, we are having this x0 transpose a y0, where these two things were fixed. I mean, we took this to be the all one vector, this to be the all one vector, and then we took this thing to sum the entries of this matrix. Now suppose A is fixed and these are arbitrary. Okay? So suppose A is in F. Suppose this is fixed, where X and Y are elements in say F in, well, suppose A is just n cross n, then from Fn cross Fn to F, define the map by X, Y, this tuple is going to X transpose A Y. Note that this is still bilinear because it's linear in both components. If you replace X by say X1 plus X2 to define column vectors in this, then this one will be X1 transpose AY plus X2 transpose AY. So it's linear in the first component. If you replace Y by Y1 plus Y2, you can easily see that this is also linear in the second component. Multiply X with some scalar. this will be multiplied with the same scalar. Multiply y with some scalar, it will be multiplied with the same scalar. So it satisfies all these properties. And in particular, this is a little bit more general than the dot product, because for the dot product, what was the matrix here? Identity matrix. So in this example, now the proposition is that well, this form which we here denote by f, will also denote it often by denote bilinear form often with just two brackets of this form, a greater than and a replacement sign. These are not exactly that, it's L angle, R angle, two brackets, angular brackets. So let's write it down using that notation. Yes. Bilinear form, an arbitrary bilinear form. So if we just write this as a map from V cross V to, we'll often say that let this be a bilinear form from V cross V to F. Okay. So, oh well, symmetric. At first we must define what is a symmetric form. You already guessed it. So, symmetric form, a symmetric bilinear form actually, is what? If Pw is equal to W P. If you interchange the first and second component, you get the same result. So the first proposition is that, consider this form now, this one. For dagger form, is symmetric if and only if
Symmetric form we have written, that's a symmetric form for bilinear map.
there is a symmetric bilinear form. Okay. By symmetric form, we are meaning a symmetric bilinear form. This one, the other form is this one. The other form is symmetric if and only if this A is a symmetric matrix.
So what do you mean by a form? Is it a map?
Yeah, a bilinear form is a map from V cross V to F. A linear map, a map which is linear in both components.
No, what is form? I mean it part and what is form?
What? But the form, well, it's a function from V cross V to F. This F we are calling a bilinear form, or we are often denoting it also by this one. This two brackets, just like you are writing F, writing this just as two brackets, not these brackets, but those angular brackets. So if and only if A is symmetric. And the proof is kind of going to be, well, at least the forward implication would be obvious. So can we wipe the spectral theorem?
Yes.
Thank you.
So basically the position is that x transpose AY is equals to y transpose AX.
Yes, exactly. Yeah. So the person I see speaking, when I turn, whoever I see speaking, will say the proof. I don't see anybody speaking. So I could hear somebody. Yes, you. Tell the proof. I'm asking you. How should you proceed from here? What's given to you? That the form is symmetric. What does it mean? W. Well, here we are working with x and y, right? So suppose x y. How is it defined? X transpose A y. And this one y transpose. Okay. Thank you. Y transpose X. So now, if the matrix is symmetric, suppose so this is, well, we want to prove that this happens if and only if A is symmetric, right? So I first note that this is an element is in Javani. This is an element where X transpose AY in R or if X transpose AY is in F. And what can you say about its transpose? The transpose of this, it's in F. And are they equal? Yes, right? It's a scalar. Yes, right. So that implies X transpose AY is equal to X transpose AY whole transpose, which is equal to Y transpose A transpose X. Okay. Right? And now, if A is symmetric, that means, this is just meaning that A is equal to A transpose, right? So that means this is equal to Y transpose A X, which is equal to Y X. So A is symmetric, that is implying, backward implication is done. That is A is symmetric, that is implying XY is equal to YX. Okay. Now, we have to get that A is symmetric from the symmetry of the form. So how should we proceed? Yes, Parun?
Say X transpose AY is equal to Y transpose AX.
Yes.
Then we know they are both elements of, they are one by one matrices in a field F.
Right.
And so the transpose will also again be equal to the original matrix. So we take transpose of one of the sides, and then we show that A transpose and A have to be equal.
Yes, but how do we get that? All the entries of A transpose are equal to all them. So AI, we call this as AI. So you have to show that that is equal to A transpose IJ, right? That is A. Yeah. So how do we get that?
So since both of them are 1 plus, I think what is it, like if both of them are 1 plus matrices, so it's interesting, like they
Yes,
transpose on one side.
if both of them are 1 cross 1, as we know that this is a 1 cross 1 thing, this is fine. Okay, and from here we are getting that. If A is a symmetric matrix, then the bilinear form in which we put input X and Y would give us the same output if we put Y and X. In the reverse order, if we put if we input these things. This one? Yes. So note that this is a scalar term. Right? If you transpose a scalar term, what do you get? You just get it back, right? It's a 1 plus 1 thing. So that means this is equal to its transpose. And the transpose of this is equal to Y transpose A transpose X. Okay. And that would be equal to this because A and A transpose are same. So we are assuming this here. And then this is equal to this by definition. Now we are only given that this holds for all X, Y in Fn. And you want to conclude that A is symmetric.
So we take a transpose. First, we can write X transpose AY is equals to X transpose AY transpose.
Yes, that's what we did
Right?
here, right?
Okay, so that is equals to Y transpose A transpose X.
Right?
Oh wait.
Then we can say like if so Y transpose.
Yes, Otto?
So we know there X transpose AY equals to Y transpose AX.
Yes.
And we know that Y transpose A transpose X is equal to X transpose A Y.
Y transpose A transpose X, yes, that is equal to?
We
this one and this one.
And
Yeah,
we take them to
you
one
equate
side
that.
and just
But
take
nevertheless,
transpose
how do you get the equality of all the entries? So indeed, these and these are true for all y and x that you know. Yes, we wrote it there. That this were the same. And then what?
When we take the minus,
And then we just take them on one side and we can write it as y transpose A transpose minus AX.
So let's write it down.
Y transpose A transpose minus AX.
X minus y transpose A x, that is equal to 0.
That
That
is
means
equal to 0. So y
y
transpose
transpose
A transpose minus AX.
A x is equal to 0,
Now
right?
if y and x are 0, then we can't compute anything. But if they're
We know
not
that it
0,
is true for all the x, y, and z.
so then it's A transpose minus A equals to 0.
Why?
No, for example, it could happen that y transpose and x are 0, but A transpose is not equal to it.
Yeah, so it's like you have to, so you all you know that this is satisfied for all inputs y and x. Okay? From here, how can you conclude that these two are equal? Up to this, it's perfectly okay. And then, yes, Vikram?
take two cases where x and y can be zero simultaneously,
Yes.
and one case where
Well, if x and y are both 0 simultaneously, this doesn't give you any new information.
yes, if one of them is zero,
So you have to specialize x and y to something.
so
To what?
one of them is zero. If either of them is zero, then I mean, irrespective of the choice of A, that is given by
Just take x and y transpose to be identity.
X and y transpose identity? You are talking about things in Fn.
Column.
Okay, wait, isn't this also a scalar?
This one, yes, it's of course a scalar. It's a scalar 0, right? Yes.
So we can decompose the x and y matrices into the components and just compare both the sides.
Well, components means
Like
want to write it down as
x1, x2, like they're
as a linear combination of the standard basis, right?
no, not standard way. These are like kind of matrices, right? Column matrices. So like I can write x1, x2, and then y1, y2.
So you just have to split. So you see that you want this from
Yes.
here.
So like I can then directly compare both the sides, right? And
Yeah. So it would be nice
If x equal
if
to y.
if you could take, no, not x equal to y, but if you could take some x and y such that which is giving you the ijth component. Can you fix x and y such that you are getting the ijth component of this matrix inside? The ijth, you see that you have to compare the ijth entry of these two things, right? So if you could get out the ijth entry of this matrix inside, so suppose you are given the choice of x and y, and you are given some matrix here. Suppose, I mean, is there any choice of x and y which will get you the ijth entry of B?
So for x we'll have the jth entry as 1 and
Right.
every entry other as 0, and for
Perfect.
the y transpose we'll have the ith entry as 1 and all the other entries.
Wonderful, yes. So that will do this. Well, so for here, I mean, let y be this one. So take the ith one. Right, yeah. So 0, 0, here 1, and the ith place. Okay, 0 everywhere else. For x, you take 0, 0 everywhere else except 1 and the nth place. So basically, x and y are the ith and jth things from the standard basis. So if you put this here, you just get the ijth entry of this, and you know that that's 0. So yes, or
So why don't we just let these are non
which one?
instead of choosing what it should be, why don't we say that x and y are not zero?
X and y are.
Not zero, like not
So you are taking some arbitrary non-zero things, x and y. Yes, it is true for all x and y. And then how do you proceed then?
then I will get that A transpose is equal to
A transpose? No, you are not getting that. How? You cannot cancel vectors from both sides, right? These are not scalars. So it's not like you are multiplying with scalars and then if it is not zero, you are cancelling. That cannot happen. You cannot. I mean, what would it mean by taking the inverse of a vector? That's not defined.
we could multiply y transpose or something.
Yes, but that would work.
Because it's a 1 by 1 matrix.
Exactly.
You're multiplying a
Yes.
column matrix.
Sir,
Yes.
so why do I check, I mean, choose some y and x such that they are from the elements from the basis?
Because you need this equality of aij and aj, right? Or you want to show that all these entries are 0. And how do you show all these entries are 0? Just choose x and y to be such that which takes out ijth entry. So the next thing is, given a bilinear form, do we always have such a representation? That is, can we always write it as x transpose ay for some a, some x, some y? Let's figure it out. Suppose V is a vector space and V is a vector space with basis V, which is V1 Vn, and suppose we were given some form. Okay? So let from V cross V to F be some bilinear form. Okay? Then we define the gram matrix of this form, or the matrix associated with this bilinear form. Gram matrix of the form with respect to the basis B. How do we define it?
Sir,
Yes.
sir, what about the converse of this?
What converse of? We need to prove it first. At first we assume the symmetry, and from this was a symmetry, and that implied that this were the same. And then we started with this one, so that was a backward implication. We wanted to obtain it first, and then from there we obtain the symmetry of the matrix. So gram matrix of the form this with respect to P. We define it in this manner. Well, define this matrix Aij as Vi Vj. So the ijth entry of the matrix is just the output of the bilinear form with Vi and Vj as its input vectors. So how does it look like? So it's this matrix A. Sorry. Here you have P1, P1, dot dot dot, P1, Pn, Pn, P1, Pn, Pn. That's the gram matrix, or the matrix associated with the bilinear form, the given bilinear form, with respect to the basis B. Now suppose you have a vector V, some arbitrary vector V in V, and then with respect to this basis B, how we could represent this V? There exists X in Fn such that this V is, well, this V is a linear combination of these elements, V1, V2, Vn. The coefficients you could write in a column, right? So you could write this as Px. P is a basis, and this column is representing the coordinates of the vector V. Okay. And then suppose you want to compute now, and suppose W in V, then that implies there exists Y in Fn such that W is equal to By, right? And what do we get now? by the bilinearity of the map, we'll have that this is equal to, well, at first let's write it down. This is summation, okay, at first. Let x be equal to c1 dot cn, y be equal to c1 dot dn, and then v is just equal to summation over ci vi, right? You are multiplying this, I mean v and this column to the coordinates. Okay? So that's it. And w is summation over j dj vj, sorry. Right? Now use bilinearity. Then you get sum over I and j, ci, dj, vi, vj. Right? What are these entries? Yes, of course, they're entries of the gram matrix. And more precisely, if you denote these entries as say aij, then you get here sum over I, j, ci, aij, dj. Right? All this is scalars, so you can of course, I mean, write this in before this and that. So what it is? It's just x transpose A, y. A is a gram matrix. Okay. So this is actually a general way of writing down any bilinear form where x and y are just denoting the coordinate vectors of the corresponding. I mean, A is the gram matrix and x and y are the coordinates of the vectors you want to multiply or you want to put in the bilinear form, as argument in the bilinear form. So yeah.
What did they actually show here? Like what?
That this kind of forms are rather general. That is, it's not just an example of a bilinear form, but every bilinear form could be brought down to this form. I mean, brought down to, written down in this form, where x and y are just the coordinate vectors of this v and w.
So the bilinear form is a function from
v cross v to x,
v,
right?
Yeah. So since x transpose and y are sort of characterizations of what we want to take as in the bilinear form. So the bilinear form is characterized by A. So can it be like two bilinear forms? If I have two different forms defined by different formulas, will I have the same gram matrix?
Well, it depends on which basis you have. So there could be two different bases, two different forms. So that's why I said that you need to formulate more precisely. But nevertheless, there could be the same form. I mean, there could be situations where the same form is represented by
two different bases. The
exactly.
same form can have a different gram matrix.
Yeah. So suppose you have two bases. Suppose you have two bases B and B dash, and you want to represent the form with respect to these two things. So how should the gram matrix change? Let's figure it out. Suppose B is a basis and B dash is another. So you know that this is the new basis, this is the old one. You want to represent this, I mean represent this in terms of this. So we have some equation like this, B equal to B dash B. And the coordinate vector, suppose B is equal to Bx, then this is just going to be B dash Bx, right? So this is going to be the new coordinate vectors of V with respect to this new basis. Okay. Now, how do we obtain this? We just took the inner products. Oh, sorry, the bilinear. I mean, put V1, V2 as the arguments of the bilinear forms. And now suppose let A dash be the gram matrix of the form with respect to the basis B dash. Then what we have? In the same situation, say we are having V and W here. So we have V, W. Well, we know that if A were the gram matrix with respect to some basis, then it would be just the coordinate vectors transposed times the gram matrix times the coordinate vectors of the next one. Coordinate vector of the first. So the coordinate vector of the first here is Px. Okay. Px transpose. Then the gram matrix is A dash with respect to B dash. So this one times Py, right? We just figure it out there. That is, if this is a gram matrix, then this would come out to be this one. And this would be basically X transpose, P transpose, A prime, P, Y. Right? But you know that VW, I mean, this form doesn't change. Just the gram matrix is changing. Okay? The form is already given to you. So you know that this is equal to X transpose AY if you take if you consider the gram matrix with respect to the previous basis B. So you are getting this equality X transpose this matrix times Y is equal to X transpose A times Y for all XY. This one? This one? Okay, we just figured it out there, right? You took this form.
So how do we know that the form is preserved while we change the basis?
We are not changing the form. We said that we are trying to represent the same form with respect to different bases, and we're just checking how the gram matrix changes.
But why do we expect the form to give out the same number?
Because the form is defined. I mean, how do you define a matrix? Sorry, how do you define a function? You define a function by its outputs, right? I mean, if you take all the outputs, wherever a form is sending the arguments, or a function is sending the arguments, that defines a function, right?
Yes.
So once the form is fixed, its arguments. I mean, if you put the same arguments, you get the same output. And now what we do here? What should we do here? We should specialize X and Y.
So just like that, you
Just I think, yeah. So what will come out then? If we specialize this to be the ith entry and this to be the jth entry of the standard basis, is equal to that one. Okay, so that's how the gram matrix changes.
So just like the representation matrix.
Yes, exactly.
That changes by PAP inverse.
Yeah. Right. And here you have the transpose instead. So you have now, so this one implies that P transpose A prime P is equal to A. Yeah, it's equal to A because you are fixing this I and j. I mean the I and j thing in the standard basis. You are getting the ith entry of this, the ith entry of this are the same. So these matrices are equal, and that would imply that A dash is equal to Q transpose Q transpose where this Q is equal to P inverse transpose. Alright. So now perhaps you could easily say what other matrices, I mean, what could be the gram matrix of the dot product with respect to other bases? What should that be? So the question is now, what order it would be from here. The matrices which represent the dot product with respect to other bases I mean, other basis means that not the standard basis, but some other basis. R of what form? Orthogonal. So, what are the matrices that represent dot product with respect to the standard basis? Identity matrix. So, just identity will go in here, right?
Yes.
So, what will it be?
Yeah.
It will be something of the form Q P transpose or P transpose P.
Acha,
So it is
so
orthogonal.
take a product we are using it.
Yeah. So,
It should be orthogonal, right?
why? It is represented dot product.
Right.
But nevertheless, you are changing the basis with some arbitrary invertible matrix, right? This P was an arbitrary invertible matrix. So all you are getting is that some matrices of the form P transpose or P transpose P.
Sir,
Yeah.
won't that